stars, galaxies, planets, moons, black holes, and all the other objects and phenomena we can observe, or even those that are beyond our current understanding. The universe is vast, intricate, and ever-expanding, containing not only the visible things we see through telescopes, but also mysterious phenomena, like dark matter and dark energy that we can't fully grasp yet. In essence, the universe is the totality of existence. It includes all the laws of nature, the forces of physics, and all the cosmic events that have shaped the universe from its birth to its present state, and everything that will unfold in the future. The most widely accepted scientific explanation for the origin of the universe is the Big Bang Theory, which suggests that the universe began as a hot, dense point roughly 13.8 billion years ago. From that moment it began expanding, and it continues to do so today. As space itself stretches, galaxies, stars, and other objects move farther apart. This expansion shapes the overall structure of the universe. The number of galaxies in the universe is staggering. For a long time, scientists estimated there were around 100 billion galaxies, but more recent studies, particularly from the Hubble Space Telescope, suggest that the actual number is much higher, roughly 2 trillion galaxies. These galaxies vary in size, shape, and structure. Some are small with only a few billion stars, while others, like the Andromeda Galaxy, contain trillions of stars. The Milky Way, which is the galaxy that contains our solar system, is just one of these many galaxies. The vast majority of galaxies are incredibly distant, often millions or even billions of light-years away. Because of this, our ability to observe the universe is limited by the speed of light. That means we can only see galaxies whose light has had time to travel to us since the Big Bang. This is known as the observable universe. Beyond that, the true size and number of galaxies remain unknown, and they may well be far greater than we can observe. The universe is immeasurably significant in several profound ways. Everything that we are, from the atoms in our bodies to the earth we live on, was born from the stars and the elements forged in stellar explosions. The universe is the context for our existence. It provides the ingredients for life. The chemical elements like carbon, oxygen, and nitrogen necessary for life were formed in stars and distributed across the cosmos, making life on Earth possible. In this way, we are not separate from the universe, but an intrinsic part of it. Our desire to understand the universe has driven scientific discovery, innovation, and technological advancements. The study of the universe through fields like astronomy, physics, and cosmology has deepened our understanding of fundamental questions about existence, time, space, and the nature of reality itself. For example, the theory of relativity by Albert Einstein transformed our understanding of time and space, and the discovery of dark matter and dark energy has opened up new frontiers of research. The universe is deeply connected to philosophical and spiritual reflections about our place in the cosmos. Humans have pondered the nature of the universe for millennia, asking profound questions. How did we get here? What is the purpose of the universe? Are we alone in the cosmos? The universe prompts us to consider our significance within the grand cosmic scale. Are we just one speck in a vast, indifferent cosmos, or is there some greater meaning to our existence? The sheer vastness and mystery of the universe evoke a sense of awe. We are aware that we will likely never be able to fully comprehend or explore every corner of the universe. Yet that doesn't stop us from trying to understand it. The ongoing exploration of space, whether through telescopes or space missions, reminds us of the infinite possibilities that lie beyond our current knowledge. There are things we cannot yet see or imagine, and that mystery itself is one of the greatest drivers of human curiosity. The future of the universe is also of great significance. While the universe may seem to be an unchanging backdrop to our lives, it is in fact a dynamic entity. The Earth's eventual fate, whether through the death of the sun, the effects of climate change, or the eventual heat death or big crunch of the universe, reminds us of the impermanence of everything. At the same time, the idea of space colonization, intergalactic travel, and the survival of our species beyond Earth suggests that the universe could hold a future for humanity. one of exploration and adaptation. The universe, with all its galaxies, stars, planets, and forces, is a vast interconnected web. Everything in the universe, from the smallest quark to the largest galaxy, is governed by universal laws of physics, such as gravity, electromagnetism, and quantum mechanics. This interconnectedness shows that we are part of a larger cosmic system, and that every action we take, even on Earth, has ripples through the universe. Our very existence and ability to understand the cosmos are bound by these fundamental forces that govern everything. The universe is not just the backdrop for life. It is the ultimate context of existence itself. Every discovery we make about it helps us understand the origins of life, our place in time, and the forces that govern everything. Whether through the study of distant galaxies, the search for extraterrestrial life, or the quest to understand dark energy, the universe is a source of endless wonder and mystery. It holds the answers to questions that have fascinated humanity for millennia, and invites us to continue exploring, learning, and wondering about the universe's true nature and our role within it. In many ways, the universe is not just out there. It is inside us, shaping who we are, what we know, and how we perceive the world around us. The universe is not just the backdrop for life. It is the ultimate context of existence itself. Every discovery we make about it helps us understand the origins of life, our place in time, and the forces that govern everything. Whether through the study of distant galaxies, the search for extraterrestrial life, or the quest to understand dark energy, the universe is a source of endless wonder and mystery. It holds the answers to questions that have fascinated humanity for millennia, and invites us to continue exploring, learning, and wondering about the universe's true nature and our role within it. In many ways, the universe is not just out there. It is inside us, shaping who we are, what we know, and how we perceive the world around us. Our solar system, the collection of planets that orbit the sun, is just one small part of the vast universe. Here's a breakdown of our planets within the solar system and some context about other planetary systems in the universe. The solar system consists of 8 planets that orbit the sun, along with moons, dwarf planets, asteroids, comets, and other smaller celestial objects. These planets are divided into 2 main groups. 1. Inner planets, also known as terrestrial planets. These are the rocky planets closest to the sun. They have solid surfaces and are made mostly of metal and rock. Mercury, the smallest planet and closest to the sun. It has extreme temperatures due to its lack of atmosphere. Venus, similar in size to Earth but with a thick toxic atmosphere of carbon dioxide and clouds of sulfuric acid, leading to extreme heat. Earth, our home planet, the only known world with liquid water and life. Mars, the red planet, with a thin atmosphere and cold desert-like surface. Mars has the largest volcano in the solar system, Olympus Mons. 2. Outer planets, which include gas giants and ice giants. These planets are much larger and farther from the sun, composed primarily of gases and ices rather than rock. Jupiter, the largest planet in the solar system, a gas giant made mostly of hydrogen and helium. It has a strong magnetic field and dozens of moons, including the largest, Ganymede. Saturn, famous for its stunning rings. Saturn is another gas giant, also composed mostly of hydrogen and helium. Uranus, an ice giant with a unique tilt on its axis, causing it to rotate on its side. Its atmosphere contains water, ammonia, and methane. Neptune, the farthest planet from the sun. Neptune is an ice giant similar to Uranus. It has the strongest winds in the solar system. Dwarf planets are smaller celestial bodies that orbit the sun, and share characteristics with planets, but don't meet all the criteria to be classified as full planets. Examples include Pluto, which was once considered the 9th planet, but is now classified as a dwarf planet. It has an eccentric orbit and is part of the Kuiper belt. Eris, Haumea, and Makemake are other recognized dwarf planets, most of which lie in the outer reaches of the solar system. Now, let's talk about other objects. The asteroid belt is a region between Mars and Jupiter filled with rocky objects. The Kuiper belt is a region beyond Neptune with icy objects, including Pluto. And then there's the Oort cloud, a hypothetical region at the very edge of the solar system, containing icy objects that could be the source of comets. Beyond our solar system, there are billions of other stars, and many of those stars have planets orbiting them. These planets are called exoplanets. As of now, thousands of exoplanets have been discovered using telescopes like Kepler and TESS. The Kepler Space Telescope, active from 2009 to 2018, discovered thousands of exoplanets in the Milky Way galaxy, many of them in the habitable zone, the region around a star where conditions might be right for liquid water to exist. Exoplanets come in a wide variety of types. Earth-like exoplanets are similar in size and composition to Earth, and are located in their star's habitable zone, where life could potentially exist. There are also gas giants, which are similar to Jupiter and Saturn, but orbiting other stars. Super-Earths are larger than Earth, but smaller than Uranus or Neptune, and may be rocky or gaseous. Hot Jupiters are gas giants that orbit very close to their stars, resulting in extremely high temperatures. The discovery of exoplanets has sparked interest in the search for extraterrestrial life, especially on planets within the habitable zone, where conditions might be suitable for liquid water, which is essential for life as we know it. Our solar system is located in the Milky Way galaxy, which is just one of billions of galaxies in the universe. The Milky Way contains around 100 billion stars, and astronomers estimate there could be even more planets, perhaps billions or more, orbiting these stars. Some of these planets may even be similar to Earth, with conditions that could support life. The universe is vast and constantly expanding. While we've made incredible discoveries in our search for other planets and potential signs of life, much of the universe remains unexplored, and there are likely many more surprises waiting for us as our technology and understanding continue to evolve. To summarize, in our solar system we have 8 main planets plus dwarf planets and other small objects. Beyond our solar system there are thousands of exoplanets orbiting other stars, some in the habitable zone where conditions might support life. The Milky Way alone has billions of stars, and the universe contains billions of galaxies, making the possibility of finding other planets and life beyond Earth exciting, and still largely unexplored. Earth, like the other planets in our solar system, formed from a giant cloud of gas and dust called a solar nebula. This cloud was mostly made up of hydrogen and helium, but also contained heavier elements that had been produced in earlier generations of stars. The solar nebula was disturbed, possibly by a nearby supernova explosion, causing it to collapse under its own gravity. As the nebula collapsed, it began to spin faster and flatten into a rotating disk. At the center of the disk, the sun began to form, while particles in the outer regions clumped together to form planets, moons, asteroids, and other small bodies. Over millions of years, dust and ice particles collided and stuck together, gradually forming larger and larger bodies through a process called accretion. Earth began as a molten mass, constantly bombarded by other debris in the solar system. This intense bombardment and the heat from the planet's own interior kept it in a molten state for much of its early history. During this time, differentiation occurred. Denser materials, like iron and nickel, sank toward the center of the planet, forming the core, while lighter materials formed the mantle and crust. This process is crucial because it created the distinct layers of Earth, such as the solid inner core, the liquid outer core, the mantle, and the crust. The Earth began to cool, and solid landmasses began to form. Around 4.5 billion years ago, a Mars-sized body, often called Theia, collided with the young Earth, sending debris into orbit around the planet. This debris eventually coalesced to form the Moon. This collision had a significant impact on Earth, not only creating the moon but also stabilizing the tilt of Earth's axis, which has influenced the planet's climate and seasons ever since. As Earth cooled, volcanic activity released gases including water vapor, carbon dioxide, nitrogen, and trace gases, forming the early atmosphere. Water vapor eventually condensed to form the first oceans, which covered the surface of the planet. These early oceans were vital because they provided the liquid water necessary for life to emerge. Life is believed to have originated around 3.5 to 4 billion years ago in the oceans. The exact process is still debated, but it likely involved simple molecules forming more complex structures through chemical reactions in the presence of energy sources like lightning or underwater volcanic vents. The earliest forms of life were microbial organisms, and over time these organisms evolved into more complex forms, eventually giving rise to plants, animals, and humans. Earth is located in what scientists call the habitable zone or Goldilocks zone of our solar system, where conditions are just right for life. This is the region where temperatures are not too hot and not too cold, allowing liquid water to exist on the planet's surface. If Earth were closer to the sun, water would evaporate, and if it were farther away, water would freeze. This narrow range of distance from a star is crucial for life to thrive. Earth has a relatively stable climate, which is regulated by the greenhouse effect. The atmosphere traps heat, keeping the surface temperature warm enough to support liquid water. Additionally, Earth has natural mechanisms that regulate the climate, such as ocean currents, volcanic activity, and plate tectonics. These systems help maintain long-term climate stability, which is essential for the development of complex life. Water is an essential ingredient for life. Earth is unique in the solar system for having abundant liquid water on its surface. Water is a solvent that facilitates the biochemical reactions necessary for life. It also helps regulate temperature and provides a medium for life to evolve and thrive. Earth's atmosphere is made up of nitrogen, oxygen, and trace gases like carbon dioxide and argon. This atmosphere serves as a protective shield, blocking harmful radiation from the sun and cosmic rays from outer space. It also helps regulate temperatures and supports life. Earth's atmosphere contains ozone, which absorbs and protects the planet from ultraviolet radiation, which would otherwise be lethal to most forms of life. Earth has a magnetic field generated by its iron-nickel core, which helps protect the planet from harmful solar winds and cosmic radiation. Without a magnetic field, the solar winds could strip away the atmosphere, as happened with Mars, which may have once had conditions favorable to life but lost its atmosphere due to the absence of a magnetic shield. Earth's plate tectonic system plays a crucial role in maintaining a stable climate and recycling important elements like carbon through the carbon cycle. Tectonic activity also contributes to the formation of landforms like mountains, oceans, and continents. It is believed that plate tectonics helped regulate the planet's temperature over millions of years, making Earth more hospitable to life. Earth continued to evolve through geological processes, including plate tectonics, erosion, and climate changes. Over billions of years, life on Earth became increasingly diverse, eventually leading to the complex ecosystems and species we see today, including humans. The entire process took billions of years, from the collapse of the solar nebula to the emergence of life and the world we know today. Earth's history is a dynamic and ongoing process with constant geological and atmospheric changes that continue to shape the planet. The formation of Earth's oceans is a complex process that unfolded over billions of years, driven by geological, atmospheric, and cosmic forces. Around 4.5 billion years ago, Earth formed from the dust and gas surrounding the young sun. Initially, the planet was a hot, molten mass, and any water present was in the form of vapor. Early Earth's atmosphere, primarily composed of hydrogen, helium, methane, and ammonia, was inhospitable to life. There was no liquid water, and the planet was constantly bombarded by meteorites and comets. As the Earth cooled, volcanic activity became a dominant force in shaping its atmosphere. Volcanoes released gases from the Earth's interior, including vast amounts of water vapor, carbon dioxide, nitrogen, and other volatile substances. This process, known as outgassing, gradually thickened the atmosphere. With higher concentrations of water vapor in the air, the stage was set for the formation of oceans. As Earth's surface cooled further, the water vapor in the atmosphere began to cool and condense. Over millions of years, the condensation process resulted in heavy rainfall. The continuous precipitation filled Earth's low-lying areas, creating the first oceans. This process, occurring over tens of millions of years, formed vast bodies of liquid water that began to accumulate in basins, gradually giving rise to the planet's oceans. In addition to volcanic outgassing, comets and asteroids that collided with Earth in its early history may have delivered additional water. These icy bodies likely contributed to the water supply, increasing the volume of liquid water available to fill the oceans. As the Earth continued to cool, tectonic activity played a crucial role in shaping the oceans. The Earth's crust began to form solid plates that floated on the semi-fluid mantle beneath. Over time, these tectonic plates moved, forming ocean basins and causing the seafloor to spread. Volcanic activity on the ocean floor further contributed to the cycling of water and nutrients, shaping the structure of the oceans. With continuous rainfall and the filling of ocean basins, Earth's oceans eventually reached a more stable state. The Moon, which formed shortly after Earth, also had a significant effect on the oceans through its gravitational pull. This created tides, which helped circulate ocean water and shape coastlines. The Earth's oceans also began to regulate the planet's climate by absorbing carbon dioxide, acting as a thermal buffer, and stabilizing global temperatures. Over time, the oceans became a key environment for the development of life, providing a stable and rich habitat for early organisms. In summary, Earth's oceans were formed through a combination of volcanic outgassing, condensation of water vapor, and cosmic contributions from comets and asteroids. Over millions of years, continuous rainfall filled the planet's basins, while tectonic and volcanic activity shaped the ocean's structure. The oceans not only regulated Earth's climate but also created conditions that supported life, making them an essential feature of our planet.
A black hole is a region in space where the gravitational pull is so strong that nothing, not even light, can escape from it. This immense gravitational force arises because a large amount of matter is concentrated in an incredibly small area. The boundary surrounding a black hole is called the event horizon, the point beyond which nothing can escape. Black holes are formed when a massive star runs out of fuel and undergoes gravitational collapse. This occurs when the star's core contracts and the outer layers are blown off in a supernova explosion. If the remaining core mass is large enough, it can collapse into a singularity, a point of infinite density with a gravitational field so strong that it warps space-time around it. A black hole is typically formed in the following steps. Star's life cycle. A massive star, at least 10 to 20 times the mass of the Sun, goes through its life cycle, using nuclear fusion to convert hydrogen into heavier elements like helium, carbon, and oxygen. As fusion slows down, the star no longer has the energy to support itself against gravitational collapse. Supernova explosion. When fusion can no longer counteract gravity, the star's core collapses. The outer layers are ejected in a powerful explosion called a supernova. The core that remains after the explosion might be dense enough to collapse further. Gravitational collapse. If the remaining core has a mass greater than the Tolman-Oppenheimer-Volkoff limit, about 2 to 3 times the mass of the Sun, it will continue collapsing under its own gravity, eventually forming a singularity. Singularity formation. The core contracts to a point where its density becomes infinite and space-time is warped to such an extent that it forms a black hole. A black hole is formed at the end of the life cycle of a massive star, which typically occurs after billions of years. The exact time varies depending on the size and type of the star, but black holes are not something that can appear quickly. They require a long process of stellar evolution. Black holes can form anywhere in the universe, but they are most commonly found in regions with a large number of massive stars, such as star clusters, in dense areas of space with many stars, such as globular clusters and galactic centers. Many galaxies, including our own Milky Way, have supermassive black holes at their centers. These black holes are millions to billions of times the mass of the Sun. For example, Cygnus X1 is one of the most well-known stellar mass black holes in the Milky Way, formed from a massive star, Sagittarius. A** is the supermassive black hole at the center of our Milky Way galaxy. The closest known black hole to Earth is about 1,000 light-years away, in the system called AA062000. This is still very far out of reach for current space exploration. While there are many black holes in the universe, they are generally spread out across vast distances, and the probability of a spacecraft or astronaut encountering one is extremely low. We have not yet developed the technology to travel to the vicinity of a black hole, and no spacecraft has been sent to explore black holes directly. Our current missions focus on studying black holes from afar using telescopes and other remote observation techniques. If a spaceship were to approach a black hole, several things would happen as it gets closer. As the spaceship gets closer to the black hole, the difference in gravitational pull between the front and the back of the spaceship, known as tidal forces, would stretch and compress it. This stretching effect, called spaghettification, would rip the spaceship apart long before it reaches the event horizon if it's too close to a supermassive black hole. For stellar mass black holes, these forces could become lethal at a distance of several thousand kilometers from the event horizon. From the perspective of an outside observer, the closer the spaceship gets to the event horizon, the slower its movement would appear. Time dilation due to the immense gravity near the black hole would cause time for the spaceship to slow down as it approaches the event horizon. The ship's crew would perceive time normally, but to an external observer it would seem to freeze as the ship approaches the event horizon. If the spaceship were to cross the event horizon, it would be unable to escape. Inside the event horizon, the curvature of space-time is so severe that all paths lead inward toward the singularity. No information, including light, can escape from this region, meaning the spaceship and its crew would be lost forever. Once past the event horizon, the crew would ultimately fall toward the singularity, where the laws of physics break down. The intense gravitational forces would cause the ship and everything inside it to be crushed to an infinitely small point at the singularity. In this region, the concept of space and time as we know them cease to function normally. In summary, if a spaceship gets too close to a black hole, it would experience stretching and potentially be torn apart by tidal forces. Time would appear to slow down for external observers, and once crossing the event horizon, it would be doomed to fall into the singularity beyond any hope of escape.
The James Webb Space Telescope, or JWST, is a next-generation space telescope designed to be the successor of the iconic Hubble Space Telescope. It's an ambitious scientific instrument that is revolutionizing our understanding of the universe, from observing the first galaxies formed after the Big Bang to studying the atmospheres of exoplanets and hunting for signs of life beyond Earth. Who made the JWST? The JWST was a collaborative project between 3 space agencies: NASA, the National Aeronautics and Space Administration, which led the project. ESA, the European Space Agency, which contributed scientific instruments and the Ariane 5 rocket used for launch, and CSA, the Canadian Space Agency, which contributed a key instrument, the Fine Guidance Sensor, Near-Infrared Imager, and Slitless Spectrograph, or FGS-NIRIS. The development of JWST spanned decades, beginning in the 1990s, and it was a major engineering and scientific effort, involving thousands of scientists, engineers, and technicians. When was the JWST made? The JWST was designed over a period of around 2 decades. Officially started in 1996, it went through rigorous phases of conceptualization, design, construction, and testing. The telescope was completed in 2021 after extensive testing and assembly, with the construction process taking longer and costing more than initially anticipated. The final cost for JWST came to around $10 billion. When was it sent to space? The James Webb Space Telescope was launched on December 25, 2021, aboard an Ariane 5 rocket from the Guyana Space Center in French Guiana. This marked a monumental moment for astronomy, as it was the culmination of decades of work. After launch, the telescope underwent an intricate deployment process, as it had to fold up to fit inside the rocket and unfold itself in space once in orbit. The deployment took about a month and was filled with tense moments for the team, as every step had to go perfectly for the telescope to be fully operational. JWST reached its final orbit at a location known as Lagrange Point 2, about 1.5 million kilometers or about 1 million miles from Earth. This is a stable point in space where the gravitational forces of Earth and the Sun, along with the centrifugal force of the telescope's orbit, balance out. Lagrange Point 2 provides an excellent vantage point for observing the cosmos with minimal interference from the Earth or Moon. How does the JWST work? JWST works by observing infrared light, which allows it to see through cosmic dust and gas that would obscure visible light. Here's a breakdown of its main components. First component is mirror. The JWST mirror has a 6.5 meter, or 21.3 feet, primary mirror, which is over 2.5 times larger than Hubble's 2.4 meter, or 7.9 feet mirror. However, this mirror is made of 18 hexagonal segments that were folded up for launch and had to be individually deployed and aligned once in space. The large mirror allows JWST to gather much more light, enabling it to see distant objects with greater clarity and sensitivity. Second component is instruments. The telescope has 4 main scientific instruments that enable it to observe a wide variety of phenomena. 1. Near-infrared camera, or NIRCam. This is the primary imaging instrument that detects infrared light in the near-infrared part of the spectrum. 2. Near-infrared spectrograph, or NARSPEC. It studies light from distant objects to analyze their chemical composition. 1. Mid-infrared instrument, or MIRI. This observes even longer wavelengths of infrared light, crucial for studying the earliest galaxies and objects that are too faint for other telescopes. 4. Fine Guidance Sensor, Near-Infrared Imager, and Slitless Spectrograph, or FGS-NIRIS. This helps in precisely guiding the telescope and assists with studying exoplanets. Third component is sunshield. It is JWST's most remarkable feature. Sunshield is the size of a tennis court, which blocks out heat and light from the sun. This keeps the telescope cool enough to detect faint infrared signals. The sunshield is made of 5 layers of a material called Kapton, designed to withstand extreme temperature variations. Fourth one is cooling mechanism. Since JWST observes in the infrared spectrum, it must be extremely cold to detect the faint heat signatures of distant objects without interference from its own heat. The telescope's MIRI needs to be cooled to below -266 degrees Celsius or -447 degrees Fahrenheit, requiring a special cryocooler for the job. Deployment in space. After launch, the JWST had to unfold like a complex piece of origami. The telescope's sunshield, mirrors, and instruments were all packed into the rocket and deployed in space over a period of weeks. The process was complex, but successful deployment ensured the telescope was able to work at its full potential. Range and capabilities of the JWST. The JWST is designed for deep space exploration. Here's what makes it extraordinary. 1. Infrared observations. JWST operates primarily in the infrared part of the electromagnetic spectrum. This allows it to observe objects that are too distant, faint, or obscured by dust to be seen in visible light. It can detect the heat emitted by galaxies and stars that formed shortly after the Big Bang, thus allowing astronomers to look back in time, nearly to the beginning of the universe. 1. Distance and time range. With its advanced infrared capabilities, JWST can observe objects that are up to 13.5 billion years old, essentially peering back in time to just 100 to 200 million years after the Big Bang. This is much farther than Hubble, which observes mostly invisible and ultraviolet light. This deep observational range allows scientists to study the formation of the first stars and galaxies. 1. Exoplanet exploration. JWST is also poised to revolutionize the study of exoplanets. It can study the atmospheres of planets orbiting other stars, looking for signs of habitability or even life. For instance, it can detect the chemical makeup of an exoplanet's atmosphere by analyzing the light that passes through it when the planet transits in front of its host star. 1. Astrophysics. It will study a variety of other phenomena, including the formation of stars and planetary systems, the evolution of galaxies, and the interactions between supermassive black holes and their environments. 1. Detection of organic molecules. One of the telescope's goals is to detect organic molecules and potential signs of life on distant planets by studying their atmospheric compositions for key gases such as water vapor, methane, and carbon dioxide. In summary, the James Webb Space Telescope is a scientific marvel, the most advanced space telescope ever built, capable of observing the universe in ways never before possible. From peering into the infancy of the cosmos to unraveling the mysteries of distant worlds, JWST is unlocking new frontiers in our understanding of space, time, and the possibility of life beyond Earth. Its deployment, after years of anticipation, marks the dawn of a new era in astronomy that will inspire generations of scientists, explorers, and dreamers. The James Webb Space Telescope, JWST, has already made several groundbreaking discoveries that promise to reshape our understanding of the universe and could have far-reaching effects on science, technology, and even society. Below is an elaboration on some of its key findings, along with an exploration of how these discoveries might affect our future, and whether JWST has found any signs of life beyond Earth. Observing the first galaxies. The James Webb Space Telescope has already made several groundbreaking discoveries that promise to reshape our understanding of the universe and could have far-reaching effects on science, technology, and even society. JWST's ability to look deeper into space, and thus further back in time, has allowed scientists to observe the first galaxies that formed just a few 100 million years after the Big Bang. These galaxies are some of the oldest and most distant objects ever detected, helping us peer back to the early days of the universe. Understanding how galaxies formed is essential for understanding the evolution of the universe. These discoveries could reveal new insights into the formation of stars, black holes, and galaxies, and could even offer clues about the conditions that might support life. The discoveries also contribute to our broader understanding of cosmology and the physics of the early universe, which could influence future technologies in fields like quantum computing, energy production, and space travel. A step closer to finding habitable worlds. JWST's advanced infrared capabilities allow it to study the atmospheres of exoplanets in unprecedented detail. For example, it has detected the chemical makeup of the atmosphere of a distant exoplanet known as WASP-39b, revealing the presence of key molecules such as water vapor, carbon dioxide, and methane. These are the building blocks of life as we know it on Earth. JWST's ability to analyze exoplanet atmospheres could bring us closer to identifying habitable planets, or even signs of life beyond Earth. Finding life elsewhere could have profound implications, not only answering age-old questions about extraterrestrial life, but potentially inspiring new fields of research and technologies for interstellar exploration. It may also push the envelope in space colonization efforts, as understanding exoplanet environments can inform future human missions to other planets. Exploring stellar nurseries and supernovae. JWST has captured spectacular images of stellar nurseries where new stars are born, and supernova remnants where stars meet their explosive end. One of the most notable discoveries is the Carina Nebula, a giant stellar nursery, which JWST observed in stunning detail, revealing star-forming regions that were previously hidden from view in visible light. These discoveries help us understand the life cycle of stars, which is crucial for understanding the formation of planets, including Earth. By learning about how stars are born, live, and die, we can better understand the origins of heavy elements, such as carbon, nitrogen, and oxygen, that are essential for life. This can lead to new insights into how life might arise on other planets, as well as how to potentially detect habitable environments on planets around similar stars. Gravitational lensing and dark matter. JWST has also helped uncover more about dark matter and the mysterious dark energy that makes up most of the universe's mass and energy. Using gravitational lensing, which is the bending of light by massive objects like galaxy clusters, JWST has studied how dark matter influences the motion of galaxies and galaxy clusters. Dark matter and dark energy remain some of the greatest mysteries in modern physics. Understanding these forces could not only reshape our theories about the fundamental structure of the universe, but could also lead to technological innovations in fields like energy, propulsion, and materials science. If we can eventually unlock the secrets of dark matter, it could lead to revolutionary technologies, potentially even affecting how we travel through space or harness energy on Earth. The ultimate goal. While JWST has not yet found definitive signs of life beyond Earth, it is leading the charge in searching for biosignatures, chemical compounds that could be signs of life, like oxygen, methane, and nitrous oxide. By studying the atmospheres of exoplanets in the habitable zone, the region where liquid water might exist, JWST is gathering the necessary data to potentially answer one of humanity's biggest questions. Are we alone? Finding life beyond Earth would be one of the most profound discoveries in human history. It would not only answer age-old philosophical questions, but could dramatically change our understanding of biology, evolution, and the potential for life to exist elsewhere in the universe. Such a discovery could also open the door to interstellar exploration. Missions to other planets and even other star systems could become a real possibility, changing the future of space exploration and possibly even offering us alternative habitats in the distant future. How JWST's discoveries could affect our lives and shape our future. The technologies developed to build and operate JWST, from advanced infrared sensors to cryogenic cooling systems, have already led to spin-off innovations that could benefit everyday life. For example, similar sensors are being used in medical imaging and environmental monitoring. Understanding how the universe works could lead to new breakthroughs in energy, communication technologies, and even space travel. As JWST helps us identify potentially habitable exoplanets, it could pave the way for future interstellar missions. The discoveries made by JWST might prompt future human missions to exoplanets or moons within our own solar system, such as Mars, Europa, or Titan, and could provide the scientific foundation for making space colonization a reality. The search for life beyond Earth is not only a scientific endeavor, but also a philosophical one. If we find signs of life, it could reshape how we view humanity's place in the universe. It could unite people in a shared mission of exploration and discovery, leading to new international collaborations and a global sense of interconnectedness with the cosmos. As we explore new planets, new resources, and new technologies, there could be significant economic opportunities. Industries related to space mining, space tourism, and interstellar communication could emerge. These new fields may drive job creation and economic growth, not just in the space industry, but in tech sectors and beyond. While JWST has not yet discovered definitive signs of life beyond Earth, its discoveries are still profoundly shaping our understanding of the universe. The information it's gathering about the early universe, exoplanets, dark matter, and stellar phenomena will have lasting impacts on science, technology, and philosophy for generations to come. The answers JWST provides could not only help us understand how the universe works, but could lead us to the next frontier in human exploration and our search for life beyond Earth. In short, the James Webb Space Telescope is opening the door to a new era of discovery, one where the possibilities seem as infinite as the universe itself.
Tsunamis are large, powerful waves caused by underwater disturbances. These waves can travel across entire ocean basins, causing massive destruction when they reach coastlines. While most people associate tsunamis with earthquakes, there are several other causes as well. Here's a breakdown of why tsunamis happen. The most common cause of a tsunami is an underwater earthquake, which occurs when there is a sudden shift or rupture in the Earth's crust. This movement happens along tectonic plate boundaries where plates are either colliding, pulling apart, or sliding past each other. These shifts can displace a large amount of water, generating waves that travel outward from the earthquake's epicenter. Subduction zones. Most tsunamis are caused by earthquakes in subduction zones. This is where one tectonic plate is forced under another, causing the ocean floor to suddenly move. When the plate pops back to its original position, it displaces a large volume of water, creating the tsunami wave formation. The earthquake causes the ocean floor to either rise or fall, displacing the water above it. This creates waves that spread out in all directions. These waves travel very quickly, often at speeds of up to 500 to 800 kilometers per hour, but they are usually only a few meters high in deep water, so they're not easily detected by ships. Tsunamis can also be triggered by underwater volcanic eruptions. When a volcano erupts beneath the sea, the rapid movement of magma, gases, and ash can cause the ocean floor to collapse, or the water above the eruption to be displaced. This leads to the formation of tsunami waves. In some cases, volcanic eruptions cause caldera collapse, where the top of the volcano suddenly collapses into the ocean, displacing water and generating a tsunami. Another cause of tsunamis is underwater landslides or landslides into the ocean from land. These can be triggered by large earthquakes, volcanic eruptions, or even the collapse of glaciers into the sea. When large amounts of debris fall into the ocean, they can displace water, sending waves across the ocean. For example, if a massive chunk of land suddenly slides into the ocean, either from the shoreline or from the ocean floor itself, it can cause a sudden displacement of water that forms a tsunami. The 2004 Indian Ocean tsunami, in part, was caused by both an underwater earthquake and a landslide in the region. In some extreme cases, the sudden collapse of large glaciers or ice shelves, known as calving, can trigger tsunamis. As massive chunks of ice break off and fall into the ocean, they displace water, causing waves that can travel long distances. This type of tsunami is rare but has been observed in polar regions where ice sheets meet the ocean. Antarctic ice shelves, for instance, have calved large icebergs into the ocean, which could lead to local tsunamis. Though extremely rare, meteorite or asteroid impacts into the ocean can also cause a tsunami. When a large meteorite strikes the ocean, the force of the impact can displace a significant amount of water, generating waves that can spread across the ocean. While these impacts have the potential to create very large tsunamis, they are much less common compared to other causes like earthquakes and volcanic eruptions. How do tsunamis travel? Once generated, tsunami waves travel at great speed across the open ocean. However, because of the vast distance between the source of the tsunami and the shore, the waves often go unnoticed at sea. As the waves approach the shore and enter shallower water, they slow down and increase in height, sometimes forming waves that can reach over 30 meters or more in some extreme cases. Tsunami impact on the shoreline. When a tsunami reaches land, it can cause massive destruction, often with multiple waves hitting the same area in succession. The first wave is not always the largest, and subsequent waves can be more destructive. Inundation. Tsunamis can flood large areas of land, damaging buildings, infrastructure, and crops. The powerful water can erode coastlines and wash away entire communities. Surged tsunami waves can move rapidly inland, sweeping away anything in their path. These waves are often accompanied by a backwash of water that can drag debris and people back into the ocean. Tsunami warning systems. Because tsunamis can be so destructive, many countries with coastlines at risk have early warning systems that use seismic data to detect earthquakes and measure changes in sea level. These systems can give people a warning, often ranging from a few minutes to a few hours, to evacuate coastal areas. However, not all tsunamis can be predicted, especially if the triggering event occurs in a remote location or if there is no seismic activity before the tsunami. So major causes for tsunami occurrence is when there is a large, sudden disturbance that displaces a large volume of water. The most common cause is underwater earthquakes, but other events like volcanic eruptions, landslides, glacier calving, and even asteroid impacts can generate tsunamis. Once created, these waves travel across oceans and become more dangerous as they approach the shore, often resulting in catastrophic flooding and destruction. Understanding these causes and having early warning systems in place is essential for minimizing the impact of tsunamis on coastal communities.
What are cyclones? A cyclone is a large-scale, organized system of clouds and thunderstorms featuring a clearly defined circulation pattern. Cyclones are a type of tropical storm that form over warm ocean waters, drawing energy from the heat and moisture of the ocean surface. They are characterized by intense winds, heavy rainfall, and the potential to cause significant damage through storm surges, flooding, and high winds. Depending on their location, cyclones are called different names: hurricanes in the Atlantic and Eastern Pacific, typhoons in the Western Pacific, and cyclones in the Southwestern Pacific and Indian Ocean. Cyclones can range from weak tropical storms to supercyclones with catastrophic effects. How and when are cyclones formed? Cyclones are formed in tropical or subtropical regions, where sea surface temperatures are high, usually around 26.5 degrees Celsius or higher. The basic process of cyclone formation involves several key steps. Warm ocean water. Cyclones form over warm oceans as the heat from the water increases evaporation. The moist air rises and creates an area of lower pressure at the surface. Convergence of air. Surrounding air rushes in to replace the rising air, and as it meets the low-pressure system, it is forced upwards. Rotation. The Coriolis effect, due to Earth's rotation, causes the rising air to spiral, creating a rotating system. This rotation is crucial for the cyclone's development. Deep thunderstorms. As the air rises, it cools and condenses into clouds, releasing latent heat that further powers the storm. This process creates a cyclone's eye, a calm center surrounded by the storm's most intense weather. Development and intensification. As long as the system remains over warm water, it can continue to intensify, increasing wind speeds and size. Timing. Cyclones typically form between late spring and early fall, during the warmest months of the year. However, they can occur at any time depending on local conditions. Where are we technologically in detecting and protecting from cyclones? Over the last few decades, advances in satellite technology, computer modeling, and early warning systems have significantly improved our ability to detect, track, and predict cyclones. Here are some key technologies used for cyclone monitoring and protection. Satellites play a crucial role in monitoring the development and movement of cyclones. For instance, geostationary operational environmental satellites, or GOES, provide real-time data on cloud formation, wind patterns, and sea surface temperatures. This information helps meteorologists predict the storm's path and strength. Advanced radar systems like the Doppler radar help track rainfall intensity and wind speed within the cyclone. These systems provide critical information about the storm's core and assist in local evacuation efforts, especially in coastal areas. Meteorological organizations use sophisticated models, such as the European Centre for Medium-Range Weather Forecasts or the Global Forecast System, to simulate the behavior of storms. These models use data from satellites, radar, and previous storm patterns to forecast cyclone paths and predict intensity. While cyclone tracking and prediction have improved, some recent cyclones have caused unprecedented destruction due to their strength and the vulnerability of the areas they impacted. Hurricane Katrina in 2005, USA. There were over 1,800 casualties. Estimated damage was $125 billion from Hurricane Katrina. Katrina was one of the deadliest hurricanes in US history, devastated the Gulf Coast, particularly New Orleans. The storm surge overwhelmed levees, flooding large parts of the city. Although the cyclone's winds were intense, The storm's long-lasting effects were largely due to flooding caused by levee failures. Cyclone Nargis in 2008, Myanmar. This cyclone caused approximately 138,000 deaths. Economic damage loss was over $4 billion. Cyclone Nargis struck Myanmar with little warning, causing widespread flooding and destruction. The storm's impact was compounded by the alleged slow and inadequate response from the military government, leading to a delayed humanitarian response. Typhoon Haiyan in 2013, Philippines. Casualties from this typhoon was over 6,300. Damage estimated was $13 billion. Haiyan, also known as Yolanda, was one of the most powerful tropical cyclones ever recorded, with sustained winds of 314 kilometers per hour, or 195 miles per hour. It devastated the Philippines, particularly Tacloban and other areas in the eastern Visayas, causing massive damage and displacing millions. Cyclone Idai in 2019, Mozambique, Zimbabwe, Malawi. Death toll was over 1,300 from this cyclone. Damage was estimated at $2 billion. Cyclone Idai was one of the worst tropical cyclones to hit southern Africa. It caused severe flooding, massive infrastructure damage, and a humanitarian crisis in Mozambique, Zimbabwe, and Malawi. Hurricane Irma in 2017, Caribbean, USA. At least 134 deaths were recorded. Damages were estimated $77 billion. Irma was one of the strongest hurricanes ever recorded, with winds reaching 285 kilometers per hour, or 180 miles per hour. It caused widespread destruction in the Caribbean, especially in the Virgin Islands and Puerto Rico, before making landfall in Florida, causing severe damage and power outages. As of now, cyclones remain one of the most destructive forces of nature, capable of causing widespread devastation. Advances in technology have improved our ability to predict and mitigate their effects, but the impacts of extreme weather events continue to challenge communities worldwide. Better preparedness, improved early warning systems, and stronger infrastructure are key to minimizing loss of life and economic damage from future cyclones.